students, welcome to the cbse chemistry lecture series. So in this video we are going to discuss about Werner's theory of coordination compounds. So in the year 1892, Alfred Werner, a Swiss chemist, was the first to study the bonding of nature in coordination compounds. He obtained a large number of complexes from the reaction between a cobalt chloride and ammonia. He is getting a various complexes based on the solution when it is the electrolyte is treated with the silver nitrate AgNO3. So what will happen means different complexes will be formed depends upon the number of moles of silver nitrate is added. Suppose if silver nitrate is added in the ratio 1:3, then the complex will be formed CONH3 6 times Cl3. That means 4 ions will be formed. Suppose if this COCl3 and ammonia and followed with the silver nitrate 1:2 ratio, what will happen means CONH3 5 times 1 Cl is replaced Cl2. Here 3 ions will be formed. And suppose, and similarly here also we have to change the number of molecules of ammonia. Here if it is 6 molecules of ammonia is okay. Here 5 molecules of ammonia. Then here 4 molecules of ammonia, and in the ratio 1:1 ratio of silver nitrate we are getting a complex CONH3 4 times Cl2 and Cl. Here 2 ions only formed. Suppose if that ammonia molecule is what? 4 molecules of ammonia. And same 1:1 ratio. See, we are getting a CONH3 4 times Cl2 Cl, and 2 ions will be formed. So he first analyzed this cobalt chloride with the changing of number of moles of ammonia. If it is a 6 moles and 5 moles, 4 moles, 4 moles. So in the presence of electrolyte silver nitrate we are getting a 4 ions. That means 3 Cl minus ions, and CONH3 6 times the whole complex is what? 1 ion. So totally 4 ions. So these are all reveals that what here in this case CONH3 4 times Cl2 Cl, 2 ions COC. So these two are looks like the same, but it is a cis-trans isomers. Cis and trans isomers. So based on all these things, the color formation of color is showing these compounds are all distinctly different compounds. First compound is a violet in nature. This compound is violet in nature or color. The next one is a purple color. The next one is a violet. The next one is a green color. Based on these color, these are all different compounds. And based on these results, the formation of the complexes we can study as follows. Based on these properties of many other such compounds in detail, he proposed a theory of the nature of bonding in coordination compounds called Werner's theory of coordination compounds. Werner's theory of coordination compounds. So let us discuss this theory one by one. Now we will discuss the postulates of Werner's theory. So in his complex COCl3 6 molecules of ammonia, I have written this type of complexes, and the structure is like this. So here he proposed the first postulate as every metal atom has 2 types of valencies. Every metal atom has 2 types of valencies, or you can say, what are the 2 types of valency? One is a primary valency. Another one is a secondary valency. The primary valency, here in this particular complex, the primary valency is nothing but the dotted Cl. So how many Cl is there? 3. That indicates the presence of oxidation state of the central metal ion. So that is the primary valency. Primary valency corresponds to, or you can say otherwise known as ionizable valency. Because when we in the water, it will be dissociated into ions as 3 Cl ions. Therefore, it is ionizable valency. Whereas in the case of secondary valency, or we can call it as non-ionizable valency. What is the meaning of non-ionizable valency? At the same time, what will happen? The 6 NH3 ligands will be attached with the central metal atom only. So that itself gives the structure of the complex. That is what we can call it as octahedral geometry. That is, therefore, it is a non-ionizable valency. Okay. Now you have to think about the primary valency. So we have to say primary valency corresponds to oxidation state of the central metal ion. And the secondary valency corresponds to the coordination number of the central metal ion. Okay. Then that second postulate, every metal atom has a tendency to satisfy both its primary and secondary valencies. Primary valency satisfied by negative ions, whereas secondary valencies are satisfied by both negative ions, or you can say neutral molecules. Okay. The third postulate, the ligands satisfying the secondary valencies are always directional property. That means that gives the shape of the molecule as octahedral geometry. So you have to think about the ligands satisfying the secondary valencies. Secondary valencies are directional in nature. Directional nature. Whereas the primary valencies are non-directional in nature. Okay. Based on all these things, the secondary valencies determine the stereochemistry of the complexes. That means the arrangement of atoms in a spatial arrangements. That itself we can call as what? A coordination compounds. Some other important observation in this Werner's theory coordination compounds. First we will take the coordination compounds do not retain any of the properties of the central metal ion or of the ligands. So thus in the case of solutions like CONH3 6 times Cl3, if you add a silver nitrate, the 3 AgCl will be precipitated. That indicates the Cl are as a counter ions. That is why it will be precipitated. It is not inside the square bracket, that is we can call this complex. That is the first observations. Suppose if the chloride ion are enter into the complex, then it loses the ionic character. Therefore, we have to think about that is if we add a silver nitrate, suppose if one Cl is replaced the NH3, then the remaining 2 Cl will be in the outside. That we can call this what? Only 2 AgCl will be precipitated. That means the 2 Cl is only counter ions. Thus, he has made some observations. The last one is it is possible to have some complexes in which some of the ligands may be neutral molecules and the rest may be the ions. Say for example, we can call it as CO, NH3 5 times Cl, Cl2. In this case, one of the ammonia ion is replaced by Cl. Then this complex we can name it as heteroleptic complexes. What is the meaning of this complex? This complex itself be having more than one ligands. That type of complexes we can call as heteroleptic complexes. So based on all this, the efforts of Alfred Werner, the coordination chemistry has emerged as a new area, or you can say new branch in chemistry, that's called coordination chemistry or coordination compounds. And also he awarded as a Nobel Prize in the year 1913. Nobel Prize in the year 1913, and this is a new area of chemistry, you can call it as coordination compounds or coordination chemistry. Lastly, we will discuss the limitations of Werner's theory. Werner's theory was able to explain a number of properties of the coordination compounds. It could not answer the following basic questions like One, why only certain elements form coordination compounds and not others? That is the first basic question. And second question, why the coordination sphere? Why the coordination sphere, or you can say entity, has a definite geometry, And the third one, why do these compounds possess a definite magnetic and optical properties? These are the basic question arises. Alfred Werner unable to answer these limitations. That's why the other theories like valence bond theory, crystal field theory, ligand field theory, and molecular orbital theory are emerged to resolve these questions. But unfortunately, we have in the syllabus valence bond theory and crystal field theory only for our syllabus. That we'll discuss in the coming videos. Thank you, students. If you have any doubts, please mention in the comment box. Thank you.